In the last lesson, we have looked at the reactivity series and how they were arranged from the most reactive metal to the least reactive metal. Now in this video, we're going to learn why is the reactivity series important and how we can make use of the reactivity series to predict many things. So once again, this is the reactivity series with the most reactive at the top, most reactive metal at the top, and the least reactive metal at the bottom. Now before we even go on, please make sure that you have already memorized the reactivity series because we're going to have to use it over and over again in the course of this video. So there are 4 things that we can use the reactivity series for. We'll look at it one by one. The first one is for the displacement of metal salts. Now the term displacement should not be entirely new. We have seen it before in the topic of periodic table, more specifically for halogens or group 7. We have learned that a more reactive halogen can displace a less reactive one from its halide salt. Okay, so if you have forgotten, please go back and look at the periodic table video under group 7. The displacement reaction of metals is not unlike that of halogens. It is where a more reactive metal displacing a less reactive one from its salt solution. So for example, now if I were to put a piece of iron metal into copper 2 sulfate salt solution, would anything happen? Let's take a look at the reactivity series and find the 2 metals involved. The first metal is iron and the second metal is copper. Okay, so from the reactivity series we can see that iron is more reactive than copper. So when you put iron into a copper salt, what is going to happen is that iron is going to displace copper from its salt to form copper metal, and then iron will take the place of copper in the salt, so it will form iron 2 sulfate. Okay, again this is not unlike the displacement reaction for halogens. So once again we will need to learn to write the chemical equation for this reaction. Iron is a metal, so the formula is just a symbol. Copper 2 sulfate has this formula. By now you should be quite familiar. Copper is a metal, so again we are just writing the symbol, and then iron 2 sulfate has the following formula. Next we need to try to balance it. If you check, it is already balanced. So lastly we need to add in the state symbols. Metals are solids, and then copper 2 sulfate, if you can recall the solubility rules, is actually soluble in water. Same for iron 2 sulfate, it is soluble in water. So this is the chemical equation for the reaction between iron and copper 2 sulfate. Now this displacement reaction is a very famous one. Now why is it famous? Because there is a very distinct observation that you can make when this reaction occurs. Why? I hope by now you can recall that copper 2 sulfate is actually a blue solution. Okay, it's actually a blue solution. So what happens when copper, the reason why copper 2 sulfate has a blue color is due to your copper 2 ions. Okay, the Cu2 plus ions present in copper 2 sulfate. Now in the displacement reaction, your copper 2 ions are being converted to copper metal. So in the solution you get lesser and lesser of copper 2 ions. So what happens is that one observation that you will see is that the blue color will fade. Alright. Next observation is that copper metal is actually a reddish brown solid. Okay, so as your copper 2 ions are being converted to copper metal, you will see a reddish brown solid appearing. Okay, and if you were to read further, you will find that iron 2 sulfate actually has a color as well. It is actually pale green. Okay, but because of the paleness of the color, usually you will not be able to see it when you perform the experiment, unless the amount of copper 2 sulfate, unless the amount of iron 2 sulfate produced is a lot, we are unlikely to see the pale green solution. Okay, so a likely observation that you will make when you throw iron into copper 2 sulfate is, number one, the blue color of the solution will fade to colorless, okay, or very pale green. Second observation would be that a reddish brown solid appears or is formed. Now, due to the very distinct observations for this reaction, this particular example is very, very often tested. Now let's look at another example now. What happens if we put a strip of copper into iron 2 sulfate? Once again, let's analyze the metals involved. We have copper, and the other metal involved is iron. Okay, so from the reactivity series, we can see that copper is less reactive than iron. So when we put copper into iron 2 sulfate salt solution, copper being a less reactive metal will not be able to displace iron. Alright, so for this particular reaction, for this particular example, there will be no reaction. There will be no visible change. The next thing that we can use the reactivity series for is to predict the displacement of metal oxides. Again, this is very, very similar to the displacement of halogens, to the displacement of metal salts. As we have learned, so a displacement reaction is one where a more reactive metal displacing a less reactive one from its oxide in this case. Now let us look at an example of displacement of a metal oxide. In this case, we are adding zinc to copper 2 oxide. So as always, let's analyze the two metals involved. We have zinc, and then we have copper. From the reactivity series, we can see that zinc is more reactive than copper. So when we put zinc into copper 2 oxide, what is going to happen is that zinc, being the more reactive metal, will push out copper from its oxide, and then it's going to take the place of copper in the oxide. Okay, so next we'll try to write the chemical equation for this reaction. Zinc is a metal, so Zn. Copper 2 oxide has the formula CuO, and then copper is a metal, zinc oxide has the formula ZnO. So the equation is already balanced, and now what's left for us to do is to add in the state symbols. They are all solids. Now the third thing that we can use the reactivity series for is to predict whether the oxide of a particular metal can react with carbon, or whether they can react with hydrogen. Okay, let us look at it in greater detail. Now let us look at the reactivity series again. In this reactivity series, the markers are not shown, so let me just draw them in. We have carbon over here, and then we have hydrogen. Now in the last lesson, we have already learn why hydrogen is sometimes included in the reactivity series, because it's there to indicate something. It's there to indicate that metals below hydrogen, they cannot react with acids. Okay, whereas metals above hydrogen can react with acids. So at this point, we're going to learn why carbon appears in the reactivity series also. So it's there to indicate something as well. What does it indicate is this, that metals below carbon, for metals below carbon, they are oxides. So the oxides that they form can react with carbon. And on reacting with carbon, what do they form? They form back the metals itself. Alright, so how about metals above carbon? For metals above carbon, the oxides will not react with carbon. Let's look at an example. So in this example, copper 2 oxide is being reacted with carbon, and we are supposed to predict whether a reaction can happen. So let's locate carbon on the reactivity series again. And then next we locate the position of the metal involved. The metal involved is copper. And then we find that copper is below carbon in the reactivity series. So what does that mean? It means that the oxide of copper, or copper 2 oxide, can actually react with carbon. And on reaction with carbon, what does it form? It forms back the metal. And the other product make a gas. Look at the elements involved. There is copper, there is oxygen, there is carbon. And since copper is already one of the product, the other product must be a compound of carbon and oxygen. So I hope you have guessed correctly. The other product is carbon dioxide. Okay, so let's practice again writing the chemical equation for this reaction. Copper 2 oxide has a formula of CuO. Carbon is a non-metal, C, copper, Cu, and then carbon dioxide is CO2. And if we check the equation, we find that it is not balanced. So how do we balance it? Is that we need to add a 2 in front of CuO, and then we need to add a 2 in front of copper. And lastly, we need to add in the state symbols as shown. Now let's go back to the reactivity series. Reason being, there's one more marker that we need to learn, and students often confuse this marker, this new marker, because it's very similar to the existing ones that are already in the series. So the new marker is here. Okay, it's just below zinc. I will indicate this marker as a H2 marker. Okay, so what this H2 marker indicates is this, that the metals below H2, the oxides of these metals can react with hydrogen gas. And on reacting with hydrogen gas, what does it form? It forms back the metal itself. Okay, so as mentioned, students often confuse this marker with the other hydrogen marker that's in the reactivity series. Alright, so please take note of the positions of these two markers and what each marker indicates. The H in the reactivity series, the H marker in the reactivity series tells you which metals can react with acids and which metals cannot react with acids. The H2 marker, okay, the H2 marker in the reactivity series tells you whether the oxide of the metal can react with hydrogen gas to produce the metal. So this is an example of what the H2 marker can help you with. So let me draw in the H2 marker. The H2 marker is over here. So what happens when we try to react lead-2 oxide with hydrogen? Will a reaction happen? So let us check the metal involved. The metal involved is lead, and we find that lead is below the H2 marker. So what it means is that the oxide of lead or lead-2 oxide can react with hydrogen gas, and on reacting with hydrogen gas it forms back the metal. And the other product, again by looking at the elements that are remaining, I hope you can see that water is the product. So let us write the chemical equation. The equation is already balanced, so let us write in the state symbols. Now in this case, in order for this reaction to happen, we need to heat up the reaction setup, and because of heating of the reaction setup, the water over here is in the form of steam rather than water. Okay, so the state symbol for H2O will be gas. Now the last thing that we can use the reactivity series for is to predict the stability of metal carbonates. Now what are metal carbonates? Metal carbonates are compounds that are formed when a metal ion combines with a carbonate ion. So for example, copper 2 carbonate. Okay, other examples would include iron 2 carbonate, sodium carbonate, potassium carbonate. So when a metal combines with a carbonate, we call them collectively as metal carbonates. Now some metal carbonates can be broken down by heat. Now remember I mentioned that it is a compound, and we have learned in element compounds and mixtures that compounds can be broken down into simpler substances by two ways, either by a current or electricity, or the other way is by heat. So over here, some metal carbonates can actually be broken down by heat. For example, copper 2 carbonate. What happens when you heat copper 2 carbonate is that it will break down into simpler substances. It will form copper 2 oxide and carbon dioxide gas. Okay, so let's try to write the chemical equation. Copper 2 carbonate gives you copper 2 oxide and carbon dioxide, and the state symbols are as follows. Now this again is a very famous reaction. It's a very famous reaction. Why? Because again it has very distinct observations that you can make. Why? It's because copper 2 carbonate has a very distinctive green color. Okay, go and Google copper 2 carbonate and you will see that it has a very nice green, bluish green color. Okay, and then copper 2 oxide is black. So what happens when you heat copper 2 carbonate is that you are heating a green solid, and on heating the green solid you will find that it turns black. Alright, with the evolution of a gas. So if you were to connect the experimental setup using a delivery tube into lime water, you will find that the lime water forms a white precipitate because carbon dioxide gas is being produced. So back to the reactivity series. What can we use the reactivity series for? Is to predict whether a metal carbonate will decompose, will be broken down by heat. And the rule is this: the more reactive the metal, the more stable is the metal carbonate towards heating. Alright, so what does it mean when we say that the metal carbonate is more stable? For example, potassium. Potassium is a very reactive metal. So potassium carbonate is extremely heat stable. What do I mean by extremely heat stable? It means that when I heat it, very strongly, it will still remain as potassium carbonate. It will not be broken down. Same as sodium carbonate. Alright, for potassium and sodium, the carbonates do not break down no matter how high we heat it to. How about the rest of the metals? The rest of the metals, for example, if we were to compare zinc carbonate versus copper 2 carbonate, okay, zinc is more reactive than copper. So when we compare zinc carbonate with copper 2 carbonate, zinc carbonate will be more thermostable, will be more thermally stable than copper 2 carbonate. Okay, so practically what does it mean when it's more thermally stable? It means that in order to decompose zinc carbonate, what does it mean to be thermal stable? It means that in order to decompose zinc carbonate, it will require a higher temperature. Okay, a higher temperature to decompose zinc carbonate compared to copper 2 carbonate, or you will need a longer time to decompose zinc carbonate as compared to copper 2 carbonate. Alright, at this point many students will ask why. Why is it that the more reactive the metal, the more thermostable is the metal carbonate? The explanation for why is not within the syllabus of O levels. Okay, in some answers that you will see, they relate the stability to the strength of ionic bonds between the metal and the carbonate. That is not correct. Okay, in order to explain why, you need to learn something about polarization, which you will only learn in A levels. So there's nothing, it's not quite possible for us to explain why using the concepts within O level. Okay, so again, there's no need for you to know why, but within the O level syllabus, you need to know that the more reactive the metal, the more thermostable is the metal carbonate. And so what? If it's more thermostable, you will need a higher temperature to decompose it, or it will take a longer time for you to decompose it.